So, we come to the last module of this course, where we discuss some applications of microwave engineering, particularly microwave communication system and some other application areas. So, in this module we cover the following topics. We give an overview of radar system, then we discuss satellite communication systems in brief, and finally we discuss the industrial and medical application of microwaves. We start our discussion with radar, where we provide an overview of radar. Radar or radio detection and ranging is one of the oldest application of microwave technology. So, in its basic form, it consists of a transmitter which sends out signal. It is reflected by a distant target and then detected by a sensitive receiver. So, if we use a narrow beam antenna, then this gives us the information about the direction of the target. So, it can be estimated from the angular position of the antenna or the beam. So, the next comes, once we have found the direction of target, next comes the distance to target, and this is determined by the time required for a pulse signal to travel to target and back to the receiver. So, this delay involved from transmission of a pulse till it is received back, that can be used to estimate the distance to the target or the range of the target. Another important parameter that we want to know about the target is the radial velocity, and if the target is moving, then the Doppler shift produced in the returned signal can be used to estimate this. So, we can see that in a radar we can know in which angle the target is located, its range or distance from the transmitting antenna, and as well as if the target is moving, what is the velocity. So, we get all information about a target. Now, radar has many application areas. So, this has been put in three verticals: civilian application, military application and scientific application. In civilian application, one major application of radar is air traffic control. Then radar is used in marine navigation, weather radar, altimetry, security alarm, speed measurement and geographic mapping. Military applications are plenty, just to name a few: air and marine navigation, detection and tracking of aircraft, missiles and spacecraft, missile guidance, fire control for missiles and artillery, search and rescue. For scientific application, we have microwave astronomy is one of the scientific application where radar is used. Then for mapping and imaging, then radar is used for precision distance measurement and also for remote sensing of environment. So, we can see that there are variety of areas where the radar finds application, and this list is not exhaustive, there are many other applications. Now, the typical frequency bands which are used for radar are VLF 50 to 330 megahertz, this is for long range surveillance. Similarly, 300 megahertz to 1 gigahertz, this is also for very long range surveillance. 1 to 2 gigahertz long range surveillance and traffic control, 2 to 4 gigahertz medium range surveillance, traffic control, long range weather monitoring, 4 to 8 gigahertz long range tracking, airborne weather monitoring systems, 8 to 12 gigahertz short range tracking, missile guidance, mapping, marine radar, airborne intercept, 12 to 18 gigahertz high resolution mapping and satellite altimetry. 18 to 27 gigahertz band is not used very much because of H2O absorption. 27 to 40 gigahertz very high resolution mapping, airport surveillance, and 40 to 100 plus gigahertz it is experimental. We now look into the configurations of radar. One particular configuration, it is called monostatic configuration, and in this configuration we use same antenna as for both transmit and receive. So, we have a signal transmitted, and here you can see a circulator. So, it will connect that signal to the antenna, the signal will be radiated. Now, we have a target, and this target will scatter the signal, and this back scattered signal will be picked up by the antenna, and this signal when it goes to the circulator, it will be delivered to the receiver, and then it will be further processed. So, this type of configuration which uses only one antenna for transmit and receive, these are called monostatic configuration. Another radar configuration is the bistatic, where we use different antenna for transmit and receive, and here the signal is transmitted from the first antenna, it is scattered back by the target, and the back scattered signal is picked up by the receiver antenna, which is given to the receiver for further processing. Nowadays, there are some advanced versions are also there, like multistatic and even multi-dynamic radar are also being tried. Let us now see the basic equation that is involved with radar. So, we have, if you consider the power transmitted by an antenna, then if Pt is the power density that is radiated is Pt by 4 pi r square at a distance r from the transmit antenna. Since the antenna has a gain G, the power density in that particular direction where the antenna has maximum gain, it will be given by St equal to Pt into G by 4 pi r square. Now, we have seen that this incident power is scattered by the target in various directions. The ratio of the scattered power to a given direction to the incident power density is defined as the radar cross section, and it is denoted by sigma. That is why in the earlier two diagrams we used this sigma while representing the targets. So, targets will be characterized by its radar cross section sigma. If Ps is the total power scattered, then we can write sigma is equal to Ps by St, and it has a dimension of meter square. Now, since the target scattered as a source of finite size, the power density of the re-radiated field decays as 1 by pi r square, and therefore, we can write SR, the received power density, it is Pt g divided by 4 pi r square multiplied by sigma, that will give us Ps, and divided by 4 pi r square, that means 4 pi r square square, that will give us the received power density. Now, this power density is incident on the receiving antenna. Depending upon the effective aperture of the antenna will receive power. The maximum effective aperture area of an antenna is related to the directivity of the antenna as effective aperture is equal to d lambda square by 4 pi, where lambda is the operating wavelength. For electrically large antennas, effective aperture area is often close to the actual physical area, but for many other type of antennas, the common ones are say dipoles or loops antenna, there is no simple relation between physical cross sectional area of the antenna and its effective aperture. So, suppose we will have a loop antenna of radius r. So, physical cross section is pi r square. What we are talking is an effective aperture. This effective aperture is different from the physical aperture, and when the incident power density at the antenna is multiplied by the effective aperture, we get the power that is intercepted by the antenna. To include the effect of losses in antenna, D is replaced by gain G, and therefore, PR becomes SR into AE with D replaced by G, and when these terms are substituted, we get PR is equal to Pt g square lambda square sigma 4 pi divided by 4 pi cube into r to the power 4, and this equation is the radar equation. As the received power varies as 1 by r to the power 4, high power transmitter and a very sensitive low noise receiver are needed to detect the targets if they are located at long distances. As there is noise received by the antenna, and also generated in the receiver, some minimum input power that is detectable by the receiver is required, because we require some minimum SNR, and this puts a restriction on the range. If this power that is required at the receiver input is denoted by P min, then we can find the maximum range or the distance as R max equal to P t g square sigma lambda square divided by 4 pi cube into P min all raised to the power 1/4. So, this gives the maximum target distance from where, if we get a backscattered signal, that can be processed by the radar and can be detected. Signal processing techniques can be used to effectively reduce the minimum detectable signal. So, this P min that we require can be very low when we employ very advanced signal processing technique, and if P min reduces, then it increases R max. One very common processing technique used with pulse radar is pulse integration, where a sequence of n received pulses is integrated over time. So, here we know that the noise is essentially 0 mean. So, if we integrate the received signal over n number of pulses, we can improve the SNR, and this SNR improvement is approximately by a factor of n. In actual radar system, factors such as propagation effects, statistical nature of the detection process, external interference often reduce the usable range of the radar system. So, we have discussed the basics of radar. We have discussed the radar configurations, monostatic, bistatic configuration. We have discussed about the radar cross section of the target, and also we have discussed the different frequency bands in which the radar operates and which frequency bands are suitable for what type of applications. Let us now briefly discuss the two types of radars and their operation. First, we consider a pulsed radar. Here we show the schematic or the block diagram of a pulse radar. So, we have an oscillator which produces intermediate frequency denoted by FIF, and also we have another oscillator which generates the main frequency F naught. Now, these two frequencies are mixed and this is a upper sideband mixer. So, after multiplying this F naught and FIF, this mixer filters out the sum of the two frequencies. So, we will have F naught plus FIF, this is filtered out, and then a signal of this frequency F naught plus FIF, it is given to the power amplifier, and output of the power amplifier is given to the antenna which radiates this frequency. Now, we can see that the antenna, same antenna is used for transmission as well as reception of the signal, and the antenna is connected to the rest of the radar system by a TR switch or a transmit receive switch, and it is operated by a pulse generator. So, when this switch is connected here, the signal having frequency F naught plus FIF, it is transmitted by the antenna, and then this switch is moved to the other location and the antenna goes in the receiving mode. So, during this period, in the transmit mode, we essentially transmit an RF pulse which is having frequency F naught plus FIF, and it is active for a duration tau. Now, this RF pulse, when it hits the target and the signal is scattered back, it is picked up by the antenna. At this moment, this TR switch is connected to this location, and therefore, the antenna is in the receiving mode. Now, in the receiving mode, this signal which is returned by the target and having frequency F naught plus FIF, of course, if it is a moving target, then we will have some frequency shift produced. It comes to the LNA, and then this low noise amplifier, it amplifies the received signal and it is fed to the mixer. Now, here we can see that this F naught is also fed to this mixer, and here again sum and difference frequency will be produced, and this mixer will give F naught plus FIF minus F naught, that means FIF intermediate frequency, and then this goes to the intermediate frequency or IF amplifier. Then this IF signal is detected by a detector. Now, this detected signal, it is given to a video amplifier, and finally, it is displayed in the display unit. So, we can see that after transmitting the RF pulse, the system goes in the receiving mode, and the total time between two pulses, it is represented by Tr, and 1 by Tr will be the pulse repetition frequency. Usually it is of the order of 100 kilohertz. So, out of this time Tr, only a small fraction of the time tau is used for transmission of the RF signal, and remaining time the system operates in receiving mode. So, it picks up the noise, clutter as well as return from the target, and it is adjusted in such a way that the target return appears when the system is operating in the receiving mode, and then the next pulse is transmitted. This Tr switch provides very good isolation, because this switch, after transmitting, it is connected to the position corresponding to receive mode, and since it is a switch, the isolation between the transmit unit and receive unit is very high. We next consider another type of radar which are called Doppler radar. So, in this type of radar, a shift in frequency relative to the transmitted frequency occurs in the return signal. Whenever the target of a radar has a velocity component along the line of sight of radar, and this shift occurs due to Doppler shift. We know that whenever we transmit signal from a source and it is reflected back by the target, and the target is a moving target, in that case, depending upon the direction of movement, it will produce a shift in the frequency of the return signal. Frequency may increase or decrease depending upon whether the target is approaching the source or it is moving away from the source. Now, the shift in frequency for a radar can be expressed as Fd is equal to 2 V F naught by C. So, we see that the Doppler shift produced depend on two parameters. One is the velocity V of the target and also the operating frequency F naught. For a given operating frequency, a higher velocity will produce larger Doppler shift. Similarly, if we are operating for the same target velocity, if we are operating the radar at a higher frequency, we will have higher Doppler shift. Now, the received frequency can be either F naught plus Fd or F naught minus Fd, depending upon the direction of movement of the target. Positive or negative sign corresponds to an approaching or receding target respectively. Here we show the block diagram of a Doppler radar. We have a signal source which produces a frequency f naught. Now, this signal is given to a circulator. The circulator connects this signal to the antenna which is transmitted, and this is the transmitted signal. Here we have the target with radar cross section sigma, and suppose this target is moving with a velocity v, and therefore, in the return signal we will have a frequency shift, and it is denoted by f naught plus minus f d. Here of course, if you consider this to be the direction of velocity, then it will be f naught plus f d, but in general it will be f naught plus minus f d. Now, when this signal is incident in this port of the circulator, by the property of the circulator, it will be transmitted to this port and not to the other port, and this signal having frequency f naught plus minus f d, in this mixture it is multiplied by the signal frequency f naught, and the difference of these two gives f d at the output of the mixture, and then this is filtered out. Now, the range of the filter or the bandwidth of the filter is set according to the maximum velocity of the target that we are going to detect. Now, this signal f d is then given to the amplifier, and finally, it is given to the display unit. We find that this velocity v, this Doppler shift f d is related to the velocity v of the target. So, a continuous wave transmitter can be used as a local oscillator for the received mixture, as the received signal frequency is offset by a Doppler frequency. The mixture is followed by a filter having a pass band corresponding to the expected minimum or maximum target velocities. The effect of clutter return and transmitter leakage at the frequency f naught is eliminated by having high attenuation at 0 frequency. So, if we have a, since we will have this mixture, we will subtract f naught. So, any clutter return and transmitter leakage around f naught will translate near 0 frequency, and therefore, we require very high attenuation near 0 frequency, and this type of filter response also helps to reduce the effect of 1 by f noise, but the approaching or receding target is indistinguishable in Doppler radar, as the sign of f d is lost in the detection process. So, here we can see that we have written here F naught plus minus F d, but thereafter after mixing operation it is only F d. So, by using a mixer that produces separately the upper and lower side band products, the above information can be recovered. A pulse Doppler radar is a form of radar which combines both the technique of pulse radar and Doppler radar. The return of a pulse radar from a moving target will contain Doppler shift, which can be used to determine both the range and velocity and also the angular position if a narrow beam antenna is used of a target with a single radar. So, by measurement of pulse delay, we can find out the range from the frequency shift produced in the signal, returned signal. We can find out the velocity, and finally, if we are using a very narrow beam for transmission, so by observing the angle of the transmitted beam, we have knowledge about the angular position of the target. A major disadvantage of the pulse radar is that distinguishing a true target and the clutter returns from ground, trees, building, etc. is a tedious work. So, if the targets are static, it is very difficult to identify the true target, but for a moving target, as in an airport surveillance radar application, the Doppler shift can be used to separate its return from clutter, which is stationary relative to the radar. So, when we have the background which is relatively stationary and the target which is moving at high speed, it is easy to detect the target. So, there are many other advanced form of radar which have been developed over the year. In this lecture, we have only discussed the very basic principles behind the operation of this radar system, and the radar systems, they employ high power sources for transmitting signals covering a very long range, and therefore, some of these high power microwave sources that we have discussed, particularly magnetron, is very useful in the context of radar.